Series of lecture we shall discuss Bessel differential equation and its solution. Bessel differential equation is one of the most important differential equation of mathematical physics. It arises from the radial equation when one wants to solve a Laplace type equation in cylindrical coordinate system. Then the row equation or the radial equation leads to the Bessel function. Bessel function has a variety of diversion, and there are textbooks which is textbooks available in international market which is exclusively devoted to our Bessel differential equation, as for example a treatise on Bessel differential equation by Watson, one of the most famous book of mathematical physics. The Bessel differential equation is this xy prime plus x square minus alpha square y is equal to 0 where prime means derivative with respect to space square x, and alpha is any finite quantity, it not necessarily any real quantity. Alpha may even be complex one. Now coming to the solution, we see that x is equal to 0 is a removable singular point. X is equal to 0 is a singular point. So according to Frobenius-Fuchs theorem, we opt for a solution like this. Summation over k is equal to 0 to infinity ck x to the power m plus k, with the restriction the c0 is not equal to 0. The index m will be obtained from Indicial equation. We differentiate it and put it in the equation. From the first equation we get summation over k ck m plus k ck m plus k into m plus k minus 1 summation over k, the first term, and the power of x is m plus k. When we differentiate it twice, the power is reduced by 2, which is being adjusted by the x square term, and then the second term gives you summation over ck m plus k x to the power again m plus k, and this if we consider if we add these two terms then and takes m plus k common, then it is m plus k minus 1 plus 1, so it is altogether becomes summation over k ck m plus k whole square minus alpha square to the power x to the power m plus k plus summation over k ck, this term is x to the power m plus k plus 2 is equal to 0. This is what we get on substituting this into the Bessel differential equation. For indicial equation, the indicial equation is there will be two initial equations. One is obtained from the coefficient of x to the power m, then only this term contributes, and that too for k is equal to 0. So in which case we get c0 m square minus alpha square is equal to 0. Since c0 is not 0, m has two values plus minus alpha. we will discuss this again. Then there is another indicial equation which comes from the value of we get by comparing the coefficient of x to the power m plus 1. Again, only this term contributes because this term starts with x to the power m plus 2 and other higher powers, and k is not, and k is essentially a non-negative integer. So we get c1 times m plus 1 whole square minus alpha square is equal to 0. We write it as c1 times m square plus 2m plus 1 minus alpha square is equal to 0. From here we know that m square is equal to alpha square, so these two terms cancels each other and we are left with c1 times 2m plus 1 is equal to 0. If m is equal to if m is equal to half, that is if m is equal to plus minus alpha by 2 or alpha is equal to if alpha is equal to plus minus half, then c1 may, this part of the board may not be visible, so we rewrite it. We get c1 times 2m plus 1 is equal to 0, and we know that m is equal to plus minus alpha or c1 1 plus minus 2 alpha is equal to 0. Now if alpha is not equal to plus minus half, then this part is not 0, then c1 is 0. So we conclude that for alpha value other than this, other than plus minus half, c1 is essentially 0. If alpha is equal to plus minus half, then c1 may or may not be 0. This is the conclusion about the C1 series. You remember that this power differs by 2, so Ck will be related to Ck plus 2, and in that case one series will start with C0 involving C0, C2, C4, etc. And other series may start with C1 and involve C1, C3, C5, etc. For values of alpha which is not equal to half, the other series, the odd series is not there. This is an important conclusion. And C1 terms, the series that starts with C1 may be taken into consideration only for alpha is equal to this, and we shall show afterwards that it is not at all necessary to consider the series starting with C1, because we can get both the linearly independent solution of this of the Bessel differential equation. Now I am coming back to the discussion on this fact. We know that there are two theorems due to Frobenius and Brooks. One theorem says that one theorem is related to the form of solution, that is when we should use power series method, if the we can apply power series method when the point of expansion is an ordinary point of the differential equation, and we can use Frobenius-Brooks method when the point of expansion is a removable singular point. In the case of Legendre and Hermite differential equation, x is equal to 0 was ordinary points, so we use power series method. In the case of Lagrange here in Bessel differential equations, x is equal to 0 are removable singular points, so we have used Frobenius method, and the unknown index has been obtained from the indicial equation. In the case of log we found that both the values of m are 0, but here the values of m are different, they are plus minus alpha. Now there is another theorem due to Frobenius and Fuchs, which says that when the roots of the indicial equation differs by an integer, then it is guaranteed that the higher root will give you a solution and the lower root may or may not give you a solution. That means if alpha is a positive quantity, then m is equal to plus alpha will definitely give you a solution. If say alpha is equal to integer or half or integer, then the value of the higher root, that is m is equal to alpha, will give you a solution. That is, if m is, and the lower root may give you a solution or may not give you a solution. I am coming to the discussion on it. First point, alpha is equal to integer, say n. Then we have two roots, m is equal to plus minus n. The plus n, we get the solution for alpha m is equal to n, the solution is known as jnx. For m is equal to n, the solution is jnx, and for m is equal to minus n, the solution is known as jnx, and we shall show afterwards that this is equal to jn of minus x. So this is not a linearly independent solution. So we conclude that the higher root indeed gives a solution, while the lower one does not give us a linearly independent solution. This relation will be required afterwards, so I am writing it in this part. The second point, if alpha is equal to half odd integer, then the value of m, delta m, the roots of indicial equation is an integer. As for example, if alpha is equal to half, then the roots of indicial equation m1 is half and m2 is m1 is equal to half and m2 is equal to minus half. So the difference is an integer. Again, according to Frobenius-Fuchs second theorem, this one will definitely give you a solution. This may or may not be give any solution. But in this case, we find that j of half x is 2 by pi x sine x, and j of minus half of x, we shall prove this afterwards. So they are linearly independent solution. So here we get both the solution by Frobenius-Fuchs method. If alpha value do not belong to either of these two categories, then both the solutions can be obtained from Frobenius method. Only in coming to the value of C1, C1 has to be considered, or C1 may be non-zero only when alpha is half. But we see that for alpha is equal to half, only the series starting with C0 can give us both the linearly independent solution. So we need not require to consider the series starting with C1 in any case, as at least for Bessel differential equation. So with this we conclude that Bessel differential equation, for Bessel differential equation, the indicial equation is very important, and here we can consider it as an illustration of Frobenius-Fuchs second method. Now we know that m is equal to plus minus alpha, and we come to recurrence relation. For recurrence relation, we start with this. We consider the coefficient of x to the power m plus k. So x to the power m plus k is from this part ck, it is m plus k whole square minus alpha square, and if we take this on the other side, this is c of k minus 2. Because this term contributes to x to the power m plus k for k is equal to k, and this term when k is replaced by k by 2, and or ck m square plus k square plus twice m k minus alpha square is equal to minus ck minus 2. This cancels, or we get ck is equal to minus ck minus 2. If we take common k common, so we get k plus 2m as the recurrence relation. Here we, and m can have plus minus alpha. So the recurrence relation is this is the recurrence relation for Bessel differential equation. Now we try to find out the coefficient, which, as we have stated earlier, we need to consider only the series that start with C0, so to say the even series, and we need not require to bother about the series starting with C1, which arises only for when alpha is equal to half, and in that case both the linearly independent solution can be obtained from the two values of m. So putting k is equal to 2, we get putting k is equal to 4, we get this is 4. If we substitute the value of C2 over here, we get plus C0 2 into 4 into 2 plus 2m into 4 plus 2m, which can be written as, in the denominator it is, if we take 2 common, so it is 2 to the power 2 into 1 into 2, and if we take 2 common from both of them, then it becomes 2 to the power 4 m plus 1 m plus 2, and in the numerator we have C0. Coming to C6, this can be written as C0 upon 2 to the power 4 2 to the power 4 factorial 2 m plus 1 m plus 2. Note that m is m may not be an integer. C6 for C6 it is minus C4, and here it is 6 into 6 plus 2m. If we substitute the value of C4, we get 2 to the power, and on manipulation we get m plus 1, m plus 2, m plus 3, c0. So we can generalize the term as c of 2k is equal to minus 1 to the power k 2 to the power 2k, k factorial, and then we have m plus 1, m plus 2, right up to m plus k, and on the numerator we have c0. We will require this expression shortly, so we we keep it here for future use, and I am coming to another aspect to be addressed. This is the recurrence relation. Now we see that there is nothing in the numerator to truncate the series. As in the case of if we had a term like n minus k, then for a particular value of k, this a particular term may get 0, and which makes the other higher order term 0. But in the case of Bessel differential equation, there is nothing in the numerator which can make it 0, which can make the numerator 0. Only possibility was c0 to be 0, which is not possible in Frobenius-Fuchs method. So we see that the series for Bessel function or the solution of Bessel function for integral or non-integral values for both integral or non-integral values of alpha is an infinite series. So as we know, for infinite series we must check its convergence. So we first test for convergence, or we use the ratio test for convergence. So we write limit k tends to infinity u of k plus 2 by u of k, which is limit k tends to infinity ck x ck, or you can use it is better to use k and k minus 2, and so we write ck x to the power m plus k, c of k minus 2 x to the power m plus 2, m minus 2. So this becomes, this part is x square, limit k tends to infinity, and for this we write, as we take the modulus, the minus sign need not to be considered, and this we have 1 upon k times k plus 2m, where and this part is x square. We know that m is a finite quantity, as we have stated earlier, so this behavior is x by k modulus square. You may and it is a convergent quantity. We may argue that we obtained a behavior like x by k in the case of Lagrange differential equation, and by comparison with the series that x to the power m e to the power x, we concluded that Lagrange differential solution of Lagrange differential equation had an asymptotic divergence. So does it necessarily mean the convergence? And the condition of convergence may fail for large values of x. So it is advisable to study the asymptotic behavior of Bessel differential equation to get ourselves assured about the convergence of its infinite series solution. So we do the thing, that is, we recast the Bessel differential equation in a suitable form from which is applicable for x is very high. So asymptotic behavior. Behavior of Bessel differential equation. What we shall do? The original differential equation is x square y double prime plus xy prime plus x square minus alpha square y is equal to 0. We introduce z is equal to x to the power minus half y of x. We introduce a function y of x is equal to x to the power minus of z of x. That is, z is a new variable. So y prime would be x to the power minus of z prime minus half x to the power minus 3 by 2 z. And y double prime is x to the power minus of z double prime. Then this is minus x to the power minus 3 by 2 z prime plus 3 by 4 x to the power minus 5 by 2 z. This is the expression for x prime and y prime. If we use all these, then we get from the first term, this must be multiplied by, so this is x to the power 3 by 2 z double prime minus x to the power half z prime plus 3 by 4 x to the power minus half z. This term is coming from the first one. Then the second term has to be multiplied with, this has to be multiplied by x. So this gives you x to the power half z prime, and this gives you minus half x to the power minus half z. And the last term is x square minus alpha square x to the power minus half z is equal to 0. You see that the x prime term, a z prime term vanishes, because the z prime term, here it is with minus sign, here it is with plus sign, so it goes. So we are left with x to the power 3 by 2 z double prime. Then the other terms are involving z. You consider this term, it is 3 by 4 with plus sign, and this is minus half. So this is 1 upon 4 plus, so 1 upon 4 x to the power minus half, and this term will has x to the power 3 by 2, and this has alpha square x to the power half z. If we divide it by this term, we get z double prime. Then this term is 1. So this is this sign should be minus. So this term is 1, and then we have 1 by 4 minus alpha square by x square z is equal to 0. Asymptotic behavior is obtained when z is very high. That is, if x tends to infinity, we call z, we represent as z asymptotic, and then we get that x is very high, x tends to infinity, this term can be neglected, and we get za double prime plus za is equal to 0, which gives you that za of x is of the form a sin x plus b cos x. So what is y? The asymptotic behavior, you see that so this has, in asymptotic region, the asymptotic behavior of Bessel differential equation is ya, which is x tends to infinity is 1 by root x a sin x plus b cos x. They are periodic oscillatory function and is being dumped by this. So we see that asymptotically the Bessel differential dies to 0, this stumped oscillatory behavior. So we come to the point that the infinite series solution of Bessel differential equation is convergent for integral as well as non-integral values of alpha. So we need not to bother about its convergence. So we will back to the series expression for the Bessel differential equation. In the next class, we shall start with this point and we will obtain the series for Bessel differential equation and apply the same to find out few low order Bessel functions.